So yeah, so I just want to say, what I have to say today is really kind of scattered because I was hoping that we could kind of go through depending on what you guys want to talk about. I mean, I went a little crazy and put way too much information so that we could talk about various things if you're interested in them. And Aaron, and I want this to be like an open discussion. So interrupt me, and I'll pause every once in a while, and we'll have uncomfortable silences and stuff to see if you guys have questions. And then Aaron, since you're the reinforcement learning connoisseur, you can interrupt me and tell me what I'm getting wrong, and
no.
or
Yeah,
add or yeah.
we can interact. That's fine. Yeah.
Let's see, Mario. Do I need to be? Should I pull my slides up? I think I need to be host, right, to do that.
No, you think you can put the slides up immediately, but I'm gonna make you host anyways.
Oh, let me see.
Or co-host, because
that's
then
okay.
we can all do everything.
Oh, also, before I begin, do you want me to do like a little background of like my scientific background at all? Does that matter?
How lovely. I mean, yes, please. I think that I haven't done it, so yes,
Okay.
yes.
It'll be
give us a few words.
All right, it'll be brief. Okay, am I up?
Yes.
All right, so I mean, I named this talk, although it really shouldn't have a name, but I named it Reinforcement Learning in and Out of Brains, because that's roughly what we'll be talking about. So let me give you my background here. This is where I'm standing right now. Like Mario said, I create the Brain Inspired podcast. It's a luxurious studio, as you can see. I don't know if you can see this, but this is the Artificial Intelligence sort of Bible, which is like a thick tome. And I basically use it to keep my microphone stand from falling over. So just like the Candell and Schwartz textbooks that you guys are probably familiar with, I could have used that as well, though I don't have a copy of it. When I went into graduate school, I'm gonna make this pretty short. When I went into graduate school, I wanted to study the lofty questions, right? Like I wanted to study the neural basis of what consciousness is. And I ended up getting, which is a hard and big question. And I ended up being accepted into the lab of Mark Summer at the University of Pittsburgh and at CMU. Mark was a great advisor in that he was really supportive of what I wanted to study. However, he used non-human primates in his lab, so I couldn't readily study consciousness in his lab. So I had to figure out, with Mark's help, like what is the closest thing to consciousness that I could study in a non-human primate in an experimental neurophysiology setting, and that turned out to be what's called metacognition, or thinking about thinking, or cognition about cognition. So already this became it's still a very hard problem, right? Hard question, but it became a smaller and narrower question. But we ended up designing a task to test metacognitive abilities in monkeys, and then to see if we could find neural activity related to that metacognitive ability. So here's the experimental setup. I'm going to take you through the task and just really briefly what we found. You have a monkey in a chair. We lowered electrodes into its brain into various areas. Monkey's in kind of a dark room looking at a screen, and we'll be making eye movements to report its decisions in this task that we created that I'm about to show you. So the metacognition task, has two phases. Each trial has two stages or phases. So the first stage is what we call the decision stage, or what you could call the cognitive aspect. And in this stage, the monkey is just trained to report where in the periphery a target appeared. So you start out by fixating a central fixation spot, and then a target appears in the periphery. The monkey's still fixating, and then very quickly masks appear at these 4 different locations. And the monkey's job is to say which of these masked locations did the target appear. So that's a decision or a cognitive task. And then the trial's not over. Then comes the metacognitive stage of the task, or what we call the bet stage. And this is where the monkey has to remember its decision and think whether it got it right or wrong, and then make a bet on whether it thinks it got it right or wrong. So this happens by after the decision is made, the monkey comes back, fixates a new fixation spot, and then two bet targets come up in the periphery, a high bet target and a low bet target. And the monkey makes a bet to report how it thinks it made its decision, whether it thinks it got it right or got it wrong. And then it gets rewarded based on how it bet relative to the decision. So if it bet high, like it got it right, and it actually did get it right, it got a lot of reward. And if the monkey got it right, but bet low, it still got a little bit of reward. But if the monkey got the decision wrong and bet high as if it got it right, it got a timeout. Okay. So this is like, if the monkey is keeping track of its decisions and is making bets that are correlated with its previous decisions, then we're happy that it's performing in a metacognitive fashion. And it was really hard to train monkeys to do this, but I did. And while after they were trained, actually during training as well, but while they're performing the task, I recorded neural activity in 3 different brain areas: supplementary eye field, frontal eye field, and dorsolateral prefrontal cortex, because we thought those areas might be involved in processing this metacognitive kind of behavior. And what we found is that only one of the 3 areas in supplementary eye field, we found correlates for the metacognition. So what I'm showing here are just 2 different conditions in the trial. This blue stripe, the blue neural activity, we examined activity during a time after the monkey made a decision, but before it made a bet. So as it was like processing, am I going to bet high? Did I get it right? Am I going to bet low? Did I get it wrong? And so this blue trace here is the neural activity on conditions when the monkey got it right and then bet as if it got it right, as if it knew it got it right. And then the red trace here is when the monkey got it right and in fact made the same decision, moved its eyes to the same location, but then later bet low as if it didn't know that it got it right. Maybe it was guessing or it had low confidence that during the decision part of the trial. Okay, so long story short, we found a handful of these kinds of neurons in supplementary eye field. But just to zoom out, this was a really cool neuron because this was a really fun day in lab. So this blue trace, I think I got it right. What I was showing you before is this interstage time, like between the decision and the bet. And it turns out, there were a handful of neurons that started to separate before the monkey even made an eye movement to the target. So if you'll remember that the target came on and the monkey can perceptually process it, right? But then we ask it to hold off making a saccade until it's cued to make the saccade. But its brain already knew, or at least this neuron already knew, I'm going to get this right and I'm going to bet high that I got it right. So anyway, this neuron separated really early in the trial, and you could even just hear it as I was recording it over the loudspeaker, and I knew this was going to be a really good neuron. Okay, so that was my graduate work. And then my postdoctoral work, I studied what's called response inhibition and in a choice paradigm. And I'm not going to take you through that, but this is just to say that that turned out to be really hard too, but it was even a smaller and more narrow question. And this is where I learned how to do some modeling. And the reason why I'm bringing the modeling up, this is a very simple model for the task, and I'm not going to even take you through it. But this is sort of the old or traditional way to model that I learned. And that is to develop a hypothesis for how you think your cognitive function of interest might be implemented in brains, for instance. This happens to be a mathematical psychological model, but then we mapped it onto brains. But so you develop a task to test a cognitive function, right? You train an organism, human, animal, organism to perform the task. That organism produces real data, and then you spend time with your model, which is the hypothesis, producing its own data and trying to match its data with the real data, right? And compare them. And then if they compare well, then you can say that you have a good model, that it's a good hypothesis. So a little bit of what I will probably be talking about today is, since the deep learning revolution, quote unquote, in about 2012, it set off this new way of using models in science, and that is to treat the model itself as the organism. So in this instance, you've trained an organism to perform a task, which produces data. So you can do the same with a model. I mean, I'm showing here like a little toy version of a recurrent neural network, which I know you guys have learned a little bit about. And that model, once it's optimized, produces data. So the model and the organism were both trained to perform the task. And then you can take the data from the model and the data from the organism and compare them that way. So this kind of approach, and I don't know how much you guys have talked about this in the class, different examples, but this kind of approach, which is loosely being called neuro AI for now, and I guess I've adopted that terminology as well, has made some progress in how we understand how brains perform various cognitive functions. So in vision and other sort of sensory domains that have these hierarchical layered structures that we know about in our brain, it turns out that convolutional neural networks, which were originally modeled after our visual systems, convolutional neural networks give a good account of how the neurons in these different layers are processing up through more hierarchical, more abstract images. I just mentioned recurrent neural networks. There's been a lot of research on recurrent neural networks and decision making and looking at the dynamics within the networks. And I think you guys recently learned about transformers, which I don't know, did you guys talk about a little bit? Okay, so it turns out that transformers, like convolutional neural networks, when you look at so transformers, as you've learned about, are often trained to predict the next word. Well, it turns out that actually correlates well with what humans seem to be doing when they're listening to stories, et cetera. So our next word prediction can be mapped on to transformers' next word prediction. Okay, so anyway, there's a lot of advancement in neuroscience using these kinds of deep learning models to study our brains. Okay, so all this to say that's background, but that kind of fancy stuff that I was just telling you about, that new approach, as I was a postdoc in a neurophysiology lab, I should have known about this stuff, decision making, recurrent neural networks and all that. But I was asking, we all get so deep in the weeds in our own questions. My questions were narrowed to to this very narrow decision making response inhibition task. I went from gambling monkeys to like a very narrow response inhibition task. And my expertise was growing deeper, but it really remained narrow. So that's when I actually decided to leave academia and a year or two later start the podcast. And that's where Mario fell in love with me. Okay, so that's my background. I guess I'll just pause here just in case anyone has any questions, but I doubt you do. Oh, thanks, Mario, for the heart. Okay, so you guys learned about reinforcement learning and basal ganglia this morning, right? Okay. So this might be boring, but one of the things that Mario and I discussed when we were talking about what I should or could talk about was, reinforcement learning in the large aspect, but also eligibility traces. Did you guys talk about eligibility traces this morning? Okay. So, all right. And I know you talked about what a reward is or could be. So we'll come back to that as well, because I'm curious as to how that conversation went. But okay, so I'm going to give you a very brief reinforcement learning reintroduction, I suppose. And if you watched any of the lectures that Mario sent from my course, then you've seen this, but it's just a very brief summary of that anyway as well.
I should just let you know quickly. In fact, in the morning, having noticed that not everybody had gotten the chance to watch the videos, I thought that they were essential. And so I took an hour of the morning to basically watch the videos with them and try to point out some critical moments so that we could discuss them.
Dang it.
Basically, like this is to say that everybody that was in class today, and even some of those that were with us in Zoom, have seen all the 3 videos.
Okay. Well, then this will be quick review, and I won't spend long on it. Sorry, I'm just trying to change where the there we go. Change where you guys are located. So I stopped looking down at you. Okay, so then you saw that, in reinforcement learning, you're taking actions, you're getting, an agent is taking actions and getting rewards and observing the world. And the goal is to develop a policy of actions to take the best actions to maximize reward. And the agent is keeping track of the value of the different actions and the value of different state spaces So I'm sorry, I'm going through this super fast because of what you just said. Okay.
I'm hoping this is getting all across.
Okay.
Guys, use the chat, okay? So if you want to you don't want to stop Paul on his tracks, like collect your thoughts and feedbacks onto the chat.
Yeah. As I'm sharing my screen, can I see the chat? Let me see. I'm sure I can. I can. Okay. So I'll keep an eye on the chat as well. Try to, and please just interrupt me if I'm going too fast or.
I'll be looking at the chat, so I'll do the mediation.
Okay. Okay. And then in model-based reinforcement learning, the agent, keeps a model of, the states of the world or the actions it is taking or both, et cetera. And then deep reinforcement learning, which is what, I actually didn't give an example of deep reinforcement learning, but maybe I will. But this will be good. I'll talk about meta reinforcement learning in a minute to continue the reinforcement learning aspect of the neuro AI world. Okay, but deep reinforcement learning is the practice of using artificial neural networks to essentially as function approximators to come up with the value functions, to come up with the policies, or to keep a model of the world. So yeah, I know that you're familiar with, well, I don't know if you're familiar with what AlphaGo is, but you've likely heard about the success of deep reinforcement learning, or at least that the world champion Go player, for instance, was beat by a reinforcement learning algorithm, AI agent. This is, just one of the many celebrated achievements in deep reinforcement learning recently. And this AlphaGo architecture has been, developed and replaced by lots of others since then. And we may come to talk about self-play toward the end. I don't have a lot of slides about it, but there's a notion in reinforcement learning called self-play that actually this version of the Go AI agent didn't use that, but a version after that started using what's called self-play and became very dominant.
I'm a big fan of Alpha Star, actually.
Alpha Star. I don't even know Alpha Star.
You don't know Alpha Star?
There's Alpha Master, Alpha Go Zero, Alpha. Yeah, go ahead.
That's they use the same thing. Well, I mean, it's for development. Go is obviously the game of Go, it is chess game, and they play StarCraft too, actually.
Oh yeah, okay.
Which is which is a much more complex game, and they actually managed to beat the best player in the world.
I've never played StarCraft, I've never played Dota, but I know that Dota is another big one in that space, right?
Yeah, definitely. And then they also now apply this to also more useful things like AlphaFold. I don't know, you must have heard it. Yeah,
proteins
that predict the structures, and now all that is actually out. It's doing good. Yeah, it's well predicted, and then open data for everybody to use, actually.
Oh, is that open source?
So sort of result. No, I don't know, not this code, but the results of it. Yeah, but of course that's something else.
Yeah, the predictions.
The predictions,
yeah. So I guess the gaming world is much more powerful, at least marketing wise, as well, for when these kinds of AI agents start to become experts at this. It's more impressive because it's more of a continuous environment instead of like a steady state Go situation where there's a clear state in every moment, every move, right? Let's see. So okay. Anyway, the success of these modern deep reinforcement learning algorithms has made people very excited, right? Maybe people in the AI world very excited. So here's the old, before the deep learning revolution, deep reinforcement learning took off. There was called what was called the reward hypothesis, that any goal can be formalized as the outcome of maximizing cumulative award, and that means sort of it could be disparate goals, right? Separate goals. But recently there was this paper called "Reward is Enough," I believe is the title of the paper, and the authors in the paper, who are DeepMind people, I don't know. I guess Alpha Star is probably DeepMind because it's everything Alpha is DeepMind. So DeepMind is responsible for that as well. Essentially said that reward is all you need I guess so. The reward is enough hypothesis kind of collapses the reward hypothesis into one thing and says this is good enough for all goals. Like all of your sub goals will come out of simply trying to maximize reward in a very broad sense. So the definition, I suppose, or the hypothesis is intelligence and its associated abilities can be understood as subserving the maximization of reward by an agent acting in its environment. Okay, so this brings us to what I didn't know that you guys were going to talk about this morning, and I assume you had a discussion about it. So, the question for us then, it's fairly easy to define a reward for an AI system with points, right? But it's less clear what a reward is for organisms. And then going back to this quote, right? It starts off with the word intelligence and its associated abilities. Well, I mean, again, intelligence is an ill-defined term as well. I mean, you can operationally define it, I suppose. But I would love to just pause here. And what did you guys come up with for the question of what is a reward this morning? What did you guys discuss? Because I don't have a good answer to this.
I love the observation to keep the uncomfortable silence hanging for as long as it has to.
Yeah. I remember there was one professor in a journal club. Boy, he was good at letting uncomfortable silences hang, and I'm not that good, but I will. I have time. So someone, I guess, needs to speak up before I go on.
Yeah, I might also be name dropping for the ones that I think have thought about this. I think that everybody looking at us right now has thoughts on the matter, but they might feel a bit embarrassed. So I'm going to start selecting names in the lottery soon, unless someone speaks up. You
want me to do it? I can do it randomly.
Oh,
I can be a jerk.
Even better. You don't know them, so just hit a name.
Oh no! What do you mean hit a name? Oh, ask to unmute. Is that what I do? All right, I'm just going to the Lorian, do you have an answer to this? What is a record? Let's do what is a reward. You can answer what is a reward or what is intelligence. I don't know if you guys have talked about that broad notion as well.
We did.
Yeah, well, I think the main message of the answer to this question was that there is no. Yeah, there are multiple correct answers, but there's no. Oh, I'm sorry. There's no answer that includes all aspects.
So did you? So were there answers that were thrown around that were not? So thanks, Lorraine. I won't bother you anymore. Eva, were you there this morning? Were there answers that were thrown around that were possibilities for what a reward could be?
I think that we talked about something that leads to accomplishing a goal or part of a goal can be seen as a reward.
So like not necessarily the candy, it's the candy, but turning and unlocking the pantry door to get the candy would be a reward itself because it's a sub goal.
If you say it like that, I don't feel like it would be a reward. But if you look at greater goals, like when you're hungry, every spoon you eat is part of a reward. So it depends on the sub-action, I think.
Very good. So did you guys quickly just come? Oh, thanks, Eva. You can mute again, so I don't have to bother you again. So did you guys quickly come to the conclusion that it's just ill-defined what a reward is, that it's hard to encompass? Gabriel, did you guys just jump to that conclusion, or did you discuss further? Gabriel? Is it Gabriel?
Gabriel, yeah.
Gabriel.
It's a bit noisy here, but I mean, we looked at it from different ways. I mean, we can talk about like dopamine, the sort of biological, like signifier of reward. There's also more abstractly, it's like something that like enforces you positively, maybe to do a behavior and action.
Isn't that so weird though, from a like sort of a human total organism, I guess psychological level, to consider dopamine a reward? I mean, it's like, I guess is dopamine a reward itself to us, or is it the signal for a reward? I'm going to call on one more person. Maud. Oh, sorry. Maud says, I should only call on people with their videos on, I suppose. Or Maud, can you unmute? Are you listening? Okay, Isa, you just turned your video on. Can you jump in?
The question about dopamine?
Yeah, well, is dopamine a reward?
In the end, it is. It gives like, when it binds to the right receptors, it gives like a great feeling or something.
But
Great.
isn't dopamine only the expectation of a reward and not the reward itself?
Well, yeah. So it turns out dopamine. I'll go through again real quickly the reward prediction error that dopamine is supposed to classically have signaled, but it turns out like everything else, dopamine is involved in tons of different cognitive functions and doesn't just have one mechanism, it seems. I don't have slides on that, so I'll go through the reward prediction error.
Yeah, I do want to add something, because I sometimes in these lectures, this particular time I didn't unpack the concept profoundly, but I pointed out to them that basically trying to get to the same content you're aiming at. It's like, what is this reward you're all talking about? If you have something that you want to achieve, how does the organism know that that's something nice to achieve? And how do the dopamine neurons know that they should fire now? So and I've crossed a bit the level spectrum, and I said, well, there's the instinctively rewardable, potentially instinctively rewardable goals, you'd like to say. I mean, basically goals that are inbuilt in us with the reward functions that we already have. Say you put sugar in the mouth of a child, it will know, like, it doesn't that it's tastier than something bitter, and that's an inherent instinctual type reward. But many of the other goals can bootstrapped over experience, as we learned what achievable functions are, and how they then become associated with dopamine is much less clear. How do you bootstrap the reward space? How do you create all of these? If all you need is rewards, how do you make one? It's one of the discussions that I was trying to tickle in the morning.
Aaron, you had your hand up. Did you put it down?
Yeah, well, I mean, I was just having another like kind of a parallel of have anybody heard of clicker training? Do you know what that is?
I don't.
So it's a way of training dogs and other kind of animals in ways that so it came from some animal trainers, where they have this little device, basically some sort of metal plate.
Yeah, that's from like Don't Shoot the Dog and stuff.
Exactly. Yeah.
Yeah.
I read Don't Shoot the Dog because I was training animals. You probably and so whenever usually you treat a dog with like biscuits and so on, and then but then in order to train them, you actually start associating the treat with this clicker, where you give a pretty loud click sound, so that whenever you click, and then you give them the reward, and slowly then you actually withheld the reward, but only once in a while you give them, and somehow that association with reward actually transferred to the click itself. So then they started to recognize that the click itself means, oh, you're doing good. And that also became a reward after a bunch of training. So somehow, as Mar was saying, that it somehow the animal learned, and actually we also can do something similar, and it's just not as clear probably. Something secondary to be a signal that you also already started getting dopamine when you hear the click, for example. So I think that's something very interesting.
Well, that's like that's like shaping behavior through like instrumental conditioning, which is it's so immediate though. So I'll come back to this, because the idea of eligibility traces, right? sort of assumes that things happen immediately like that. Like, I don't know what Candy Crush, I don't know what you guys play. I've never played Candy Crush either, but these like phone games and stuff where you just get the immediate feedback. I don't know, Tetris, you guys are too young for Tetris probably, but there are games like that where you get these immediate rewards. But most of the lofty goals that we try to perform, right, long-term goals, there aren't those immediate rewards. So then how do you connect the, once you achieve the goal of becoming a professor or something like that, how do you look back and assess all of the steps that it took, and reinforce that behavior if you want to become a professor in a different subject? I mean, that's a bad example because you tend to not become professors in multiple subjects often.
Unless you're Gary Edelman.
Right. Yeah, there are plenty of exceptions, I suppose. We'll have to, maybe he'll be a test case. I was trying to come up with a good example of this, maybe building a tree house for my children or something, where there are lots of different steps, like what screws to use, how to deal with the bark and level things and stuff like that. Sorry, so Marty, I'm just looking at the chat. So what were the actions until you got a reward? You have to think back. Okay, so anyway, I'll have a few things for us to kind of. The answer is I don't know the answer, but I'll have a few things for us to step through to kind of think about this, and it'll be thinking out loud essentially. So you guys continue to jump in, please, because there's really I don't really have an agenda on this, but I'm going to go through kind of what I have in the service of generating discussion and thoughts. Okay, so I mean, obviously computers and humans are different, right? So our brains, I know you guys talked about embodiment. Our brains are in our bodies are in the world. And, we evolved. Not only did we evolve, but someone was mentioning something earlier about a baby, and it made me remember, that we develop too. And a reward for a baby is different than a reward for an adult, right? And so for a computer, it's just not clear what the analog of development is. There's training, but it's training for a well-defined objective function, for instance. And the baby's objective function changes, right, through development. Anyway, we can come back to that as well. So, but we, evolved to survive and to reproduce, and then tell the machines what their reward is, so that they can be quote unquote intelligent. So it's just a very well-defined environment for computers, because we can define their reward just via points or bits, right? So the other thing that I've been thinking a lot about recently, and I don't have a coherent story about this, is, does that mean that, so we're autonomous, right? And we're autonomous agents that, need to solve these complex problems in super messy worlds where we define the problems essentially. I guess in robotics, you get out of the well-defined problem space of, what's in like a neural network or computer, but we still define their objective functions. We still define the algorithms that they use to learn. And as autonomous agents, those objective functions aren't defined for us. They evolved, right? And in some sense, we have to select them over time. So, there's this nagging feeling in me that, there's something missing in artificial intelligence. And now I'm really just kind of thinking out loud, but, wondering, is there some way to connect our autonomy and our agency? Is that necessary for what we really consider intelligence? And that depends on what we really consider intelligence as well, of course. And then that gets to the question, well, does that mean that life is actually necessary for what we would consider true intelligence? So this is, kind of a big project trying to connect. If I want to answer yes to those things, it's a fairly large project, but it's an interesting topic to me right now. Okay, in any case, going back to deep reinforcement learning. It's very exciting. And Mario, go ahead. Just interrupt me too.
To point out that to continue on the topic of what is human knowledge and how much is given to us, like in our Bauplan, in our blueprint. Mm-hmm. Here, when they write in the Nature article, mastering the game of Go without human knowledge, there is one very important place where we have to put knowledge before this works. I was wondering if the students know what's the to what extent is this title a bit odd, like given what Paul just said? I mean, anyone has a guess? Sorry to jump in with a question.
Please, this is great. I prefer this.
Sandra, do you have an idea? Are you actually online now?
Yes.
Yeah.
I mean, the first thing that strikes me as odd is without human knowledge. I mean, human input has been put into the system. So human intervention is what made the whole thing to begin with. So can you really say that it's without human knowledge, like at all?
Well, you could at least, let's say, put it like this. Once, I guess that the idea here, but you're right. So like, I have to first off confess, you're right. I don't know what Paul thinks, but I was even thinking more narrowly about reward itself. So clearly humans had to put a lot of knowledge in terms of the structures of a neural network, in terms of the backpropagating procedures that took the rewards into the structure of the network and so forth and so on. But in addition to all of these assumptions, like I think you'd like to point out, there is a fundamental assumption about what is the state to be rewarded. And so where is the reward coming for AlphaGo?
Well, but you're just saying that AlphaGo needs somebody to teach them the game, basically. Like, what is
not the game, because they will claim that the game has been learned, like the rules.
Well, how to play the game, yes, but the rules and what is winning, for example.
What is winning? So this is what I was getting at. Yeah. So what is winning has to be very narrowly and very strictly defined, because else there is nothing.
Can you imagine a Go agent feeling bad for his opponent and losing on purpose, and that being a goal, for instance? Have you ever done that? Have you ever lost something on purpose? I mean, I have children, so I lose on purpose all the time. Yeah, that's a good point. So Mario, you wrote in the chat that you'd say that we discover our problems. And this keyed me into some of the work by people like Laura Schultz. It's not going to mean anything to you, but who has this hypothesis about the role of play growing up as a child, that one of the reasons children, let's say, evolved, you can always make a just so story when you're talking about evolution, but one of the reasons why children play is that they're inventing problems for themselves to solve, right? And that this will help them later in life when they are in some real world situation and they have to either recognize what the problem is to solve, and or they will have invented these problem spaces and worked on solving them as young children. So it's a pretty interesting hypothesis, about the function of what play is. And we don't stop playing as adults, or most of us don't anyway. I guess we slow down, but so we're constantly continuing to invent problems as practice, perhaps.
Do you want to bring it also the exploration, exploitation thing? Because I think definitely it's a prime example of plenty of exploration in childhood, and when you're adult, you actually try to exploit what you have learned.
Yeah, but even in exploration, there are sort of these unspecified fuzzy goals, aren't there? Like you're exploring something because you already have like intermediate levels of fun with what you're exploring. So in a sense, there's a bit of a hedonistic gradient as children, it seems to me, like when I look at, but I
feel like it's nature creating new rewards so that kids would actually go explore. That's how
right,
I view it.
Touch a nice texture, touch something with a good temperature, like feel the weight of something, see the consequence of throwing something somewhere. So these causal models that we have to build feel so much more unsupervised than like strictly reward based. And I think that what Paul was pointing out before is like, you can have concurrent objectives that you can't solve simultaneously. You can't both win the game and make your children happy. But those are absolutely fully decidable objective functions. Going just a bit back, so much in evolution is about not about winning, but about being viable, right? So it's about having a sufficiently stable form that can withstand the world, but there's so many solutions to that problem. And so similarly for reward spaces, it seems to me that part of the reward space is expressed by our embodiment, in a sense, one could think evolutionarily, but ultimately the objective functions themselves, the rewards themselves, they don't feel very well specified. They feel more like they're bootstrapped from something more basic.
Well, and part of the when people are worried about AI taking over the world, right, it's because the rewards that they're seeking aren't aligned with what we want them to do. But we humans, we make poor decisions all the time. So our own objective functions get us in trouble, right? Too many drugs, too much sex, too much rock and roll, and that sort of stuff. Yeah. So, well, I don't know what that adds to the actual conversation, but the
it adds a lot. I mean, Yasha was mentioning the other day to me in private conversation that he thinks that the more access we have to hedonistic outcomes, the flatter the reward surface becomes, and the more we will be the more jaded we'll become, in a sense, but also the less attracted to all of these rewards, and perhaps even more thoughtful, more metacognitive about them. But that was, I thought, was a very positive light he cast, and I thought that
I thought you were going to go the opposite way and say with a flatter surface that nothing is that attractive. So you're not attracted to the right rewards, and any reward will do because it's a flat surface.
Yeah, I guess that what there are two ways to see this clearly, and I think that then it's a matter of preference again. One of the questions that I asked in the morning was, can you choose your preferences, or do they just come to you?
And what's the answer?
So the students, like at least those that responded, I didn't feel like any conviction anyway. Did you guys rethink the question now? Like, what do you think now?
I mean, this is almost like a free will question as well, which is, that's a slippery slope.
Yeah, let's not go there.
Yeah.
But I guess that, I guess that it's from introspection, I'll tell my opinion. I cannot choose my own preferences. They come to me as a function of what I do, most definitely. And I'm aware of the fact that they're coming to me via consciousness. And I can even create a narrative that I was responsible for those preference changes. But it does feel to me like they are consequences rather than causes. Like my consciousness didn't impose that I should like bananas now. Sandra has her hands up.
In a way, I would say that preferences are maybe just a different type of action that the agent takes. So you can say that the agent takes action based on the value of different outcomes, but then a preference could be one of those outcomes. Like you have different options for preference, and then you land on a certain preference based on its own values. So maybe it's just a deeper layer of the same idea.
I think that people would generally say that a preference is kind of a value and a value function. So it's the implicit mapping that you have between states and what you would like to do. So I think you're right. It's like a potential to an action. So or the potential connections between actions and their respective personal subjective rewards. Don't think it's an action per se, but I think more like a potential to an action. Would you agree with that? I'm curious.
Yeah, that's kind of what I was trying to convey, but in not as good wording.
Thank you.
What do you all think? So I don't know if you know who Robert Sapolsky is, but he comes to mind in this discussion. And he wrote the book, I think it's called Behave. It's a really large book, but he's a behavioral, I don't know what he is. Anyway, he studies behavior and how neuromodulators, the book is called Behave. anyway, one of his conclusions is that a or the function of our prefrontal cortex, I believe he words it as like this, is to do the right thing when the right thing is the hard thing to do. And that reminds me of, if we have some sort of reinforcement learning function that is valuing some action or some state space, then we have this sort of executive canceling ability by our prefrontal cortex that says, no, don't follow that preference. If preference is a value function, don't follow that preference. You need to do this thing. And I don't know how the definition of preference sits within that sort of overriding function of the prefrontal cortex relative to our more base level value functions that we're having to deal with.
So can I jump in with a thought? In the basal ganglia, in the network we talk about the subthalamic nucleus as being the final sensor, and there are few papers on the topic, and if I would consider that how the subcortical structures often learn first and then pump into cortex, it might be that the prefrontal cortex censorship is a deferral from a earlier, more basic subthalamic nuclear function. But maybe that's too deep, too involuted, too hypothetical for this to be of any value. But I just thought it was interesting with the censorship idea.
Yeah, that is interesting.
We didn't talk
Brian.
about the free. Whenever we talk about decision making, the slippery slope of free will is really hard to avoid. And I definitely did not put anything explicitly in the curriculum about it, but I think that in this context, everybody should be considering free will. I now have a personal curiosity. How many of you have heard about Lee Bates experiments? Just out of curiosity, can you go for like thumbs up and thumbs down as emoting for Libet?
I think it's pronounced Libet.
Libet,
I think.
most likely.
Oh, should we? There.
Good. Don't go there. So there's more no's than yes. So let's not go in there.
Okay. That's a whole lecture.
Maybe you can
That's a whole.
explain that.
Sorry, Maxime.
Mario or you, Paul, maybe you can guys briefly explain the experiment for us.
Okay, I can briefly explain it. Essentially, Libet had people sit in a chair. This is missing lots of details. Sit in a chair and measured. I think he was measuring. Well, there have been. Let's say he's measuring EEG. I don't know. I don't know if what Libet was actually measuring. It might have been skin
Definitely
response.
EEG. Yeah,
It was EEG.
Event-related potential. Yeah.
Okay, it was event-related potential. He had people basically sit there with their fingers over a button, look at a clock, and he said, whenever you want to, press the button. And so they would press the button, right, whenever they wanted to. So they had free will to press whenever they wanted to. And then note on like what time it was on the clock. So they'd press and they'd say, I pressed it at 30 seconds, right? And then Libet went back and analyzed the neural data, and he could decode from the neural data, hundreds of milliseconds before. And this has been shown in different ways, like even up to like 10 seconds in fMRI signals, before they made that free will decision, before they made the decision to freely press the button. Yeah, 300 to 500 milliseconds, Mario says. Before that, their brain knew what they were going to already do. So this was considered evidence against us having free will. And there's been lots of spilled ink about how to actually interpret the neural data and the behavioral paradigm and stuff that has gone back and forth. Does that make sense?
Okay, so but then it means that humans do not have any free will at all, as decision already made before we even think about those. Or is it just a wrong experiment, or the results are wrongly interpreted, or like how would you look at that?
Yeah, so I was going to say, Gabriel, in the in the chat, one thing Libet himself suggested is that we have what Gabriel's calling free won't. So that is the ability to cancel. So even though our brain has made the decision to do it, we can still cancel it, right, at the last second, which is something that I studied actually, but I never in the context of free will. But there have been other various criticisms, and I'm afraid we're going to get down the rabbit hole of free will now. So I don't know if we need to move on or if it's break time or what. We're free to censor. Yeah.
So what we could do is this: we could open the next 5 minutes for a free will discussion for anyone that wants to. Else, people that need to go to the bathroom go, and then come back, and then I think that we resume with the second part in say 10 minutes, like when it's 5:05. What do you guys say? Make sense? And so if Maxime and others want to go down the free will slippery slope, I think that this is a perfect time. Like we can continue talking about.
Full disclosure, I am not an expert on all of the criticisms and proponents of the Libet experiments and those that have followed. So
I remember that people had complained about the clock, but like you pointed out, these days, if you have like a clear event-related trigger from which you can accumulate the neural function, because ultimately you're making averages, right?
It's averages.
You're
That's one
separating
of them.
the data from when you did and when you did not, and so the early indications of your decision come early in the day, and you might not have them completely explicit to yourself, Maxime. But what is free will? I mean, gotta have to this. If we're going the slippery slope, it does feel to me that we have a commitment with a definition, and it could be very fuzzy. I don't know.
There are also, like, you can imagine a scenario when someone's sitting. Sorry to just jump in, but I just had this thought that, all of the trials that were collected, that were analyzed, like what Mario just said, that they were averaged, right? So every time you press the button, you're going to have a different EEG signal. And, maybe you have like a different two distributions, right? One that happens right after, and then like some that happened before. And maybe the ones that happened before are like, well, maybe I should press it. I'm considering it, right? But they're all kind of aligned. They happen to be aligned to when you do press it. And then otherwise they're all scattered. But when you average them, it looks like you decided to press the button and it made the decision beforehand. The other thing I was going to mention is that I don't know how you could collect trials where to align to anything when you don't press the button. You can imagine sitting in the chair as the subject thinking, oh, should I press it now? I'm about to press it, but you never press it. So then there's nothing to align the signal to. So you have no data. It could be that the ERP, that is the signature of the lack of free will, the signature of your upcoming decision without your free will, it could be that happens to some other cognitive process that's happening when you're actually not pressing the button, right? But there's nothing to align it to in the experiment. So the experiment can't address that. So that's just off the top of my head. So event-related potential is ERP, in case I didn't say it.
I think in the Joy of Why recently, I had Steven Strogatz talking to someone. Was it in the Joy of Why, or it was the Quantum Magazine podcast? I forget. But definitely someone claiming that what was it? Protein expression. They could predict decisions in the motor system. So I feel like it's. Thank you for giggling, because this is exactly how I feel. It's like, aren't you coercing then your data to for some sort of headline? And the experiments are great. I mean, but at the same time, it doesn't feel like something new has been revealed. Don't know if you guys are following this discussion. Can you nod negatively if you're not?
I mean, the main thing to take home, though, is that it's an unresolved question, right? Whether we really have free will or whether we don't. I mean, philosophers have been debating this since time immemorial, right? Go ahead.
I think one thing is clear, like consciousness is a post hoc evaluation of what you did. So it's hard to imagine.
That's clear?
I'd say so, right? Because there's nothing that we can do but observing thoughts or ourselves or the world. And all of this is post hoc.
But you don't think a function of consciousness is to also guide future actions? Certainly,
but through a funny throw catch that happens in the past.
Mm-hmm.
Which is my beef with many people that overuse the word prediction.
Mm-hmm. Mm-hmm.
Because prediction, like reward, is one of these very big umbrellas, very big buckets. When I juggle, I don't really predict where the ball is going to fall, even though I need to have my eyes open.
Well, you mean consciously predict.
There's a set of, I guess that there's a lot of, say, entraining to an action that is described as being a prediction, which to me, I would prefer keeping them apart. But that's I do notice that it's splitting hairs a bit. I mean, like I do have this tendency to try to create specific. Just a second, I haven't answered me. I have 15 people in class. No, you can't go. So there shouldn't be a debate about who takes our child today, but apparently there was one.
Oh,
apologies.
I should have stopped sharing my screen also. I'm sorry, but I guess it's late in the game now.
Yeah, I don't think that's a problem. So predictions and rewards, what I often warn my students is that they should be very careful with the semantic space that we traverse. I mean, people are very quick to put keywords together and make a very general looking statement about how the brain works. And yet what we then need to do is look at the detail. I mean, like to what is the implicit definition of a term in a certain usage. So if you're talking about, prediction in that context, look at what it actually means. It often is a rate, a gradient in a differential equation. So it will tell, that direction, this direction, that's a direction. That's not a prediction. And like I've had like intense discussions with Wolpert about this. And I feel the mathematicians might lack the semantic sophistication sometimes.
Yeah, but isn't that the beauty of using mathematics? Because it's formalized, it doesn't actually matter what you call it, right? So, I mean, this is the computing brain course. So in the end, it's what the equations say, but it's a matter of mapping that onto a semantic space in our brains and trying to figure out, are our brains really doing this mathematical function? If so, how? If not, how not? How do they approximate it if it seems like they do? So you can take it, I think it was Yal Niv one day who framed it to me like this, about the beauty of mathematics in studying like computational processes, is that you can formalize it in math and then go and look in the brain. It's NIV, Yael NIV is her name. And then play with it in mathematics world, and then you can play with it in brain world and then bring it back into the math world. So the math world isn't real in that sense, but it formalizes something that you may be able to say about brains. And then you go see in the brain what's actually happening. And that's the really hard, I guess it's all hard, but then you can bring it back into the mathematical world eventually. And, back into the not real world, but the very formally useful world. So yeah, I've been having, go ahead.
Yeah, I wanted to react on that because recently we had Joshua Bah telling us all about formal languages. And to an extent, I think one of the messages in his talk is how much all of these formal languages emerge from our own beings. So, and I think that in that context, I wanted to tie in with the discussions with the mathematics. I do think that the mathematics gets expressed at a certain level. I do think that, however, that we still stumble upon the specific definitions of what are rewards, what are predictions in the mathematical language, because even in the mathematical, so mathematics is a set of relationships. Are you familiar with between our lived experience and some sort of generalization over the lived experience that our brains can concoct?
Sorry, are you asking me if I'm familiar with the distinction?
Yeah, the question is, are you familiar with the work of Lakoff, George Lakoff?
I have not read the celebrated Lakoff.
Nunez.
Lakato. Yeah. Okay, I thought you were talking about metaphors.
So the one that I know is where mathematics comes from. So
No, I'm not familiar.
Yeah, so what I liked about that one is that he, describes most of the formal elements of mathematics as being abstractions and generalizations over our everyday experience, like metric spaces, like real numbers, like integers, how these different number spaces interact or may not, because sometimes it's hard to make them interact because they're not about, some are apples and oranges, but some are about time. So, you have unit problems which look like physics. So you can't make some spaces interact with each other, or you have to then produce product spaces between different sensory-like mathematics.
Wait, is the idea, I'm sorry, I'm a little confused. So you said that mathematics is an abstraction over generalizations, but then before you said you related it to our lived experience, which by that I assume you mean our Umwelt, our perceptual, how we can perceive the environment and the affordances that the environment affords for our actions and stuff. Is that?
Well, yeah, both at the level of physics, basically seeing something falling is a sufficient training data to produce the mathematics of vectors, let's say. So whenever, or compositionality between vectors, that's an idea that is suggested by experience, right? So
Okay.
if you add, things like that.
Does that mean that mathematics is real? That math is real, or is it discovered or invented? What's their
In the case of Lakoff and Nunez, there is absolutely no ambiguity whatsoever. It's all discovered.
It's all discovered. Because if it's part of our lived experience, then it
is
the mathematics
with respect to.
Yeah, but then is it ontologically real? I guess it doesn't really matter if because I thought you're going to say it was invented, but because it's based on our lived experience, then we invent it because it's an abstraction over our generalization.
Yeah, I think it emerges from us. That would be my take on it. I'd say that self-organizing matter, like brains or other types of self-organizing matter, have this ability to absorb the history of perturbations. And if the perturbations come from a well-structured universe out there, like the world, then these perturbations will leave their imprint in the self-organizing matter. Now, in the case of brains, you have like temporality being very crucial, and so these variables that are the emergence of the structure of the world through our brains reflects the brains themselves in a sense, or their what they can do, the ways in which they are able to calculate, which
it's like
space and time. Basically, it's all space and time, everything, convergence, vectors, semantics, vector spaces, everything that I can think of falls within a certain the rules of our perceptual spaces.
It has to be that way because that's the way that we think. That's the way we can think based on our brains.
Constraints. Yeah, universe and brains, like the way the brains emerge from the universe and us.
I want to segue a little bit. I don't know how much time we have, but I got reminded coming from how mathematics and how we think. One thing that is kind of coming up, I don't know, in the last 1 or 2 decades, how long it is the last step of how going from what we have in AI now to a generalized artificial intelligence.
The last step.
Yeah. Not last step, one big step that is needed, or thing, but what people are saying is the one big missing element is the idea of causality, like what causes what, because now a lot of things are mainly we put in mostly correlation and things like all to understand, like, well, actually this is a very human thing to do, like, oh, if I do this, something happens, and so the kind of causality, and that is actually a big step for AI to need to implement it. And well, I mean, the thing is now, because you need to so what I'm leaning to it is that now there's so book I would just say that I was reading a book which is the Book of Why, which is authored by one Judea Pearl, is a great scientist who formalized the like how to mathematically formalize causality. Like how can you infer things based on those correlations, and you have a certain sort of model, but you like
how Piano had done that.
Huh?
You know, the axiomatization of the natural numbers is an axiomatization of causality.
Exactly. So that is whether like can an AI invent more numbers, for example, that's the one thing. But on the other hand, like so in order to code in causality, you need a way to mathematically write it down so that you can actually put it into an AI. And so that is one thing that they have been proposed or like developing. And actually, it could also be a very nice teaching tool for people to understand how science works, because I think also as human beings, we don't really understand why we think things are, and to formalize it would also be like yeah, if that happens, then all of us scientists, will get replaced, but we're still safe from jobs at this moment.
On that thought, I'd suggest let's take up the thread of reward learning again, and keep in the back of our minds that we, very soon gonna all be replaced.
Okay, so Mario, maybe you can help guide me here, because I originally we should skip around, right? So I originally was going to talk about Mars levels, which I don't know if you guys talked about in the course. And relate that to why reinforcement learning has been so successful, has been considered so successful. Maybe I can just skip that then, and I'll skip the TD learning and dopamine, and unless you want me to go through that.
I did
you watched that.
So there was one duality that I personally think is interesting and needs some unpacking from the neuroscience and from the AI perspective. So the basal ganglia, it is now the seat of many of the questions that we now have in reinforcement learning and in neuroscience, I would say, right? And it has this dual nature. On the one hand, it's supposed to do action selection, but on the other, it's supposed to produce rewards. Do these things come together? I mean, do we see more clarity in neuroscience where we have to go with respect to models to recreate basal ganglia type functions, or should we just sidestep that completely and think about softmax output function or binary output functions as a sufficient representation of action selection, and just do the learning abstractly? So if the question makes sense.
Are you asking me?
So yeah, so you asked me orient more or less where we go, and I thought, well, there's this dual thing about the basal ganglia, both like the action selection bit and the reward computing bit. Mm-hmm. So even, people watched your videos and they saw, you went from habitual behaviors to instinctive-like behaviors to high. I forget what's the name of the high-level
goal-directed. I think
that's the goal-directed, and I was wondering how these are encoded in basal ganglia. I mean, do we have some inlays in there?
So maybe this will be. I was going to talk about how the reinforcement learning system interacts with other cognitive systems and other cognitive functions. And I wonder if that would be a good place to go
I think so.
To start to address these things. But I was going to do it. Okay. I was going to do it in the guise of, or jumping out from eligibility traces, just because you had mentioned you had questions about eligibility traces. Maybe I'll go through that a little bit about eligibility traces, which I know you guys have already seen. And then I'll talk about how the reinforcement learning system interacts with other cognitive functions and systems, with a few different other ones. And we can pick it up from there. Does that sound too long-winded? I mean, I can kind of skip through stuff too.
No, on the contrary, I think that, people also wondered how rewards are backpropagated and whether that's plausible with respect to brains.
Okay. Yeah. Well, I mean, I put one example of that in here. So I'm pulling at some of the headlines you can kind of ignore, but this is just about eligibility traces, right? And you guys have learned about plasticity and how it's complicated. So you have a presynaptic neuron with its axon and a postsynaptic neuron with its dendrites. You fire an action potential, right? And there's a lot going on at the synapse, right? When that action potential reaches the terminus of the axon, it releases neurotransmitters into the cleft. I mean, these are just a few of the what people call machinery, but a few of the things going on. There's different kind of calcium uptake and release. On the postsynaptic side, you have lots of different types of receptors. Anyway, a lot of this, works together to somehow help us learn, right? And the idea is that the synapse is plastic, and that leads to learning. And then you guys learned about the 3-factor learning rule that suggests that synaptic tagging happens, or eligibility traces, right? So the idea is, like in a Hebbian plasticity scenario, if you have a spike coming in from a presynaptic neuron and that postsynaptic neuron spikes just after it, or depending on the spiking rule, depending on the plasticity rule, in proximate duration to this presynaptic neuron, then that basically tags the synapse and says, all right, let's see, was that good or was it bad? Was that action good or bad? And then along comes dopamine, for example. If it's an unexpectedly good, then there's going to be a bunch of dopamine, right, that says, whoa, that was good. And because the synapse is tagged, then it becomes strengthened, right? And you're more likely to perform that action later in, say, the basal ganglia. But actually, eligibility traces, evidence for them, they're, even though they're short, has been found in all over the brain, right? In various parts of cortex, in the basal ganglia itself, in the hippocampus. So there's evidence for this 3-factor learning everywhere in the brain. So Mario was talking about backpropagating a learning signal, and in the course and on the podcast. So, well, in AI and neuroscience in general, the backpropagation algorithm has been so successful in AI that people have been searching for it or an analog of it in brains. So one of those people who have provided a suggestion is Peter Rolfsema and his group, who's actually kind of near you guys, right? So anyway,
I did mention of his work.
Oh, you did? Oh, okay. Well, this is
only a percent.
Yeah. Okay. So here's his story about how synaptic tagging and or eligibility traces might come in and help answer the backpropagation in brains story. So how do we know which synapses to update and which direction to update them? So his idea, he and his team's idea, is that there's this feed-forward pathway that eventually, through the basal ganglia, cortex, thalamus loops, right? And eventually, there's some output action, right, of these three, let's say these 3 different actions. This final action was selected. So the idea is that there are these recurrent connections that are somehow connected to that feed-forward pathway, right? So and after you take the action, the idea is that this feedback pathway essentially tags the feed-forward pathway and says, get ready, because the dopamine we may discover that was better than expected or worse than expected. In other words, the reinforcement learning signal is about to come, and you're eligible to be updated as a synapse, right? And then soon thereafter, sure enough, a reward prediction error happens, and the synapses get updated. So this is I think it's a plausible account. And if that's not clear, anyone jump in and ask me. Peter's group also showed that when you do it this way, when you do a lot of different ways, it sort of replicates what backpropagation does in neural networks. But when you do it this way, it also replicates what backpropagation does in neural networks. And an attractive aspect of this account is that it's neurally plausible, which is a phrase that gets thrown around a lot in this kind of computational approach, right? So anyway, the neural plausibility of these things is always debatable, but this seems like a pretty plausible mechanism. And given what you guys have learned about the feedback loops in basal ganglia, right, coming from different areas of the cortex that are roughly associated with different kinds of cognitive functions, it seems like a plausible thing to implement in basal ganglia loops. But So this is where the trickiness comes in, and the clicker shaping, right? Where you click, give the reward, click, give the reward, click if you're getting closer to the reward or object, right? And that's always immediate, but eligibilities, these traces don't last long. So if I'm building a tree house for my children, and I make a few mistakes along the way, I make a few better than expected steps, and do I keep track of all that? How do I know the next time I build a tree house, when this tree gets struck by lightning and I have to start over again? How do I look back on those steps, right? So this is a problem. Okay, so this is where the interaction of the reward learning systems in our brains with other cognitive systems and other parts of the brain and other cognitive functions may come in. And of course, I don't have an answer to this question, and this is a question that Mario posed to me. I'm sorry, I was not looking at the chat here. Peter Rolfsma.
There's nothing. I'm just trying to add to what you're saying so that people have the references, but you had the name in the slide, and so I had to correct myself.
Yeah, okay. I can send these slides if anyone wants them as well.
Yes, please.
Right. Okay, I'll have to take all my comments out, which are, I'll send the slides as a PDF or something. And maybe I'll add the references to be clear as well. Okay, so anyway, what a lot of research has started to and continued to discover is that our actions we're not just reinforcement learning systems. We have lots of other ways to make decisions, right? And whether those are ultimately guided by reinforcement learning is maybe an open question. But the question maybe for discussion, and if we don't run out of time here, is there a story to tell about these interactions between reinforcement learning systems and other systems? Is there a story to tell about how eligibility traces might actually happen over the long-term kinds of behaviors, connecting the long-term behavior with that immediate synaptic firing? Okay. Maybe the first thing to say before I start talking about reinforcement learning systems interacting with others is, oh no, I covered this in the lectures. But anyway, I can reiterate just, there are different kinds of reinforcement learning systems happening in your brain, right? There's model-based, there's model-free, and the extent to which these, it used to be thought that these two systems were either one was operating independently of the other, or they were competing. Now there's a lot, or maybe it's a hybrid of the two, or they're running in parallel, and then somehow there's like a switch that's saying which output, which value estimates you should take. So anyway, that's just to say that the story of whether the brain is running a model-free or model-based reinforcement learning algorithm in different contexts is one open story, but there's been a lot of work. So another thing and I'm actually going to have Ann Collins on my podcast in November at some point, so this was kind of convenient, but yeah, please, guys, just jump in anytime and ask for any clarifications. One of the things that Ann has shown is that when you tax the working memory system, I'll talk about this in just a second. When you tax the working memory system, you're actually making decisions using your working memory and not your reinforcement learning system. So your decisions are based on what's happening in your working memory. So the way, and we don't need to go through this task in detail, but the way Ann tested this, Ann and her colleagues like Michael Frank, they developed this task where essentially you need to associate like a different shape with a different action, right? And remember it. And then you get probed, like, what is this? What's the action to take on this shape? And then you take the right action. And then sometime later, after some delay, it comes again, right? And then you can answer correctly on that. So you can either answer correctly or incorrectly on the different actions. And you can make the working memory aspect of the task harder, right? So you might have then different colors associated with actions, and two colors this time, a bunch more of shapes or colors to keep in mind, right? So your working memory is working hard during this task. And what they found, they developed a model to account for this that incorporates, it's a reinforcement learning component fused with a working memory component. And there are different weights that you can put to how your working memory is contributing to how reinforcement learning algorithms are contributing. In this case, it's a model-free reinforcement learning algorithm. And what they showed is that if you are really good, if your working memory is really good, you perform really well, even when it's hard at the beginning, but it actually slows down your reinforcement learning because your actions aren't dependent on using your reinforcement learning system, right? And in the background, meanwhile, in the background, your reinforcement learning system is learning to value, to pair the actions with the values of all these different systems, so that in the long run, and I won't get into the details, but they show this, the model's predictions match the behavior of people participating in this task. In the long run, your brain is relying more on what your reinforcement learning system has learned, because then the reinforcement learning system, which is notoriously slow, has learned over the long run to associate these actions with their values, and you don't need to rely so much on your working memory. But the interesting and somewhat troubling thing to me is that I pride myself on having a fairly decent working memory, and I guess I'm a slow learner. And I guess in this story that makes sense. Anyway, maybe that's what I can blame it on, is I have a superior working memory, so I learn very slowly. Was someone going to jump in? I thought I heard. Okay. So anyway, this has led, there's been other work with attention as well. And this has led Ann Collins and her colleagues to suggest that maybe the way that they interact, like attention and working memory, these executive functions, is by working as a filter, essentially, over the state space. So, you remember that in reinforcement learning, you get these observations from the world, and those observations are the state space of the world, right? But in real life, this is a super high dimensional state space. And depending on the complexity of the reinforcement learning problem, it may be untenable. It may be too high dimensional. So one of the things that working memory could do, or attention could do is essentially filter out the state space and feed that into the reinforcement learning system. I guess in an account like this, if your working memory or attention, if the filter was really good and was only sending just a few things that the reinforcement learning system should pay attention to, then the reinforcement learning system doesn't really get to model the entire state space, and maybe that's why it takes so long. I don't know. That was just off the cuff. But the same thing with the action space, right? So what reinforcement learning system is operating over state spaces and action spaces. So the same kind of executive function could filter out of all of the possible actions you could take in that policy that you're trying to develop, that your reinforcement learning system is developing, which are the important ones to focus on and to give weight to. Oops. Okay, so let's see, it's 9:28. I was going to talk about meta learning. Let me, I have a long introduction to it though. I think it's worth talking about just because in the course, those lessons kind of lead up to examples like this. Okay, you know what? I'll just go through it pretty quickly. And Mario, just tell me to shut up or to move on if I need to. Okay. So one of the problems, I'm just motivating this in terms of AI. So one of the problems in AI is that deep learning networks learn like very narrow tasks, right? In general, and so it's difficult to generalize to other tasks. And this is an age-old problem. So typically, deep learning networks will learn the first task that you give to them, and then you give them a brand new task, and they completely can't perform it, right? So this is called catastrophic forgetting. You become an expert at some task, and then you give it a new task, and the model has to start over because its trained net weights are no good anymore. And of course, humans generally perform something like this, right? They use like their previous experience on previous tasks to bootstrap and to learn more quickly given other tasks. So in AI, this is called lifelong learning. It is the name given to different kinds of algorithms that are used to address, how to generalize better, right? And I'm not going to go through these, but one of them is meta learning, and essentially what all these lifelong learning approaches do is, typically outside of the lifelong learning domain, typically what you do when you have a neural network is you train it on a bunch of training data just on one task, and then you test it, right? So all these lifelong learning approaches, they have like a handful of tasks, and they all have, their various training data, and just the different lifelong learning approaches intermingle like the training and testing sets in different ways. And they're just different approaches to train these networks to try to generalize them. And meta learning does it in a very specific way, in one of those specific ways. So I'm sorry, I'm also skipping over some of the details here. Okay, so the idea though in lifelong learning strategies, including meta learning, is that when you learn the structure of a set of tasks, they're typically kind of related tasks, then the previous tasks should help you generalize to future task structures, right? So if I'm at a casino and I go up to a two-armed bandit, which is like a slot machine, often this is called a bandit task, and I pull the left lever and it gives me a reward, and then I pull the right lever and it doesn't. Okay, so then I go to a new slot machine, and maybe now I pull the left lever a few times, there's no reward, but the right lever always gives me a reward. So at this point, I think, all right, this kind of bandit is deterministic, right? I just have to figure out which of these levers is going to give me a reward. So I've kind of solved this task structure in some sense, so that when I walk up to a third machine like this, I can just try once. And if it gives me a reward, I'll just pull it the whole time, right? Because I've learned the structure of these kinds of tasks. Okay. That's kind of a meta learning strategy. So it's learning to learn, learning the task structure of these different kinds of tasks. So I'll just kind of walk through how meta learning was implemented in a deep reinforcement learning system, and how that maps on to potential brain areas that may be of interest given your recent discussion in the course. So in this task, right, the task was set up, the agent was set up to perform a multi-armed bandit task, like I was just saying. And there are different probabilities given to the different levers in the bandit. And instead of, as the agent, they used a deep network, right, to perform the task, to learn the policy of the task and to learn what actions to take. And in fact, they learned what's called they used a recurrent neural network, which you've learned about. I don't know if you've talked about long short-term networks, but it's a way.
No, but one of the final projects is going to bring it back up, and I think it's fine to mention. Yeah.
Anyway, yeah, LSTMs, long short-term memory networks, have these more stable kinds of memories than typical recurrent neural networks, and that's likely why they used the LSTM. And what was input to the LSTM was the observations of the state space, also the last action that the agent performed, like which lever was pulled and whether it received reward, and then of course it output actions based on the value. And so what they did, they trained it on a different set of probabilities, right? So it's kind of a narrow task structure, but they trained the network to learn different tasks, different probability spreads of the multi-armed bandit task. And then what they did was they used deep reinforcement learning, right? So here's the deep part. The LSTM is a deep learning network. And then they used reinforcement learning as what they called a slow outer loop to train the LSTM. And the idea, and the LSTM was this fast inner loop that was updating its policy and action values, et cetera. And what they found is that the LSTM learned so that they trained it on these different task sets for a while. And then they went in and they turned off the training in the LSTM. So they froze the weights. So the LSTM could not be updated anymore. All it could do is perform the task that it was given. And then they asked the network to perform a new distribution task, like a new two-armed bandit task that had a different distribution. And what they found was that, do I have it? You've seen the reinforcement learning. Okay, so what they hypothesized was that this slow outer loop might correspond to this dopamine reinforcement learning system carried out by the basal ganglia and subcortical structures, right? And that the fast outer loop might correspond to something like prefrontal cortex, where there are lots of dopamine projections. And of course, as you guys learn, there's lots of loops with the basal ganglia and cortical and thalamic loops. And essentially what they found was, first of all, that the network could perform the new task. So it somehow generalized that task structure. But then they went in and probed, they looked at the activity in prefrontal cortex of primates performing this task, monkeys performing this task. And they came up with a proportion of units that were correlated with how much reward, the value, and the action as figured out through the reinforcement learning algorithms and computations. And then they asked what proportion in the LSTM, what proportion of units were correlated with the same things. And they found, again, that they matched quite well to the brain. And there's lots of other analyses they did. But the take home was that, do I have a slide on this? No. So the take home was that the dynamics, so you froze the weights in the deep learning structure. And the take home was that it was slowly trained through the reinforcement learning algorithm that even though now it didn't have to update at all, it could learn a new task structure just via the dynamics within its recurrent neural network. That's a mouthful, but, and it's kind of hard to, for me, it was kind of hard to wrap my head around how dynamics themselves could be considered learning a new task.
That's why I bring the echo-state networks every time I teach recurrent neural networks, because the latent space of the network is a complex manifold that has specific, like a sets of trajectories. I've given them a very early 1998 paper that has shown that randomly recurrent neural networks basically already contain complex, like chaotic type trajectories.
These are the liquid state machines, liquid state.
Echo state networks, liquid state machines, potato. Yeah. Those
are cool. Yeah. Okay, so anyway, go ahead. Sorry.
No, I was going to say that, the fact that behavior is not all learning is something that I'm always thinking about. What's the time scale of learning, but the time scale of behavior. As a computational neuroscientist, I often say that what I'm trying to explain is like 3-4 minutes of behavior. Take a network, take that structure, take that state in the structure of your brain, and it will produce behavior, even if you're not learning, or at least I surmise, I hypothesize. And so the 2-3 minutes of interesting behavior that your short-term memory gives you is in the dynamics of the system. Like you have stored, you have stored the state and you're acting upon that state. You didn't store like loads of new information yet. You just basically absorbed the state space outside of you. So sort of like profiled and sampled it, and that's all percolating the system without altering its structure.
Yeah, very good. Okay, so I have just a couple more, and then we'll just pause and discuss for the rest of the time here. So that was more on the short term, working memory and training a shorter term network like the prefrontal cortex over the state space. But there are also interactions between reinforcement learning and longer term. And I do have some slides here. I don't have pretty slides, but something called episodic reinforcement learning. And the idea is roughly something like this, right? So when we're a brain or an agent, a neural network interacting in the world, we perform an action, that output has some value, right? And the idea is that we can store the state of the world and that value in our memory, right? In an area like our hippocampus. And then later, when we're confronted with some situation and need to perform an action, we can query this memory bank, however large it is, and then just perform a calculation, a dot product or something on a matrix, and say, how similar was this situation to that situation? And then instead of using, having to calculate a reward signal and in order to choose an action, if it's a really similar situation and already had a high value, then we can just output the same action, right? So in this sense, we would not be using, just like Mario was just saying, in this sense, we wouldn't be using our reinforcement learning system or learning at all, but just rote memory or some episodic like memory. And of course, there have been a bunch of networks that have done that these days, and I won't go over the details because there's, essentially you have to figure out how to write to that memory, how to read from that memory, how to compare that memory to the ongoing situation. But this has kind of become standard in a lot of deep reinforcement learning models these days as well, to have this episodic memory kind of component. So I'm saying all of this in the service of keeping eligibility traces in mind, just so that we can kind of think about like how these processes might interact. Okay, so I think the last thing that I'll talk about is, did you guys cover complementary learning systems? Okay, so you didn't. One of the things that has come out of neuroscience that has also been very useful in artificial intelligence is the idea of replay, which I'll talk about in just a second. So the idea is that our brain uses two complementary learning systems. One is very fast, and we memorize episodic events, right, or individual memories. And this is the idea is that this is encoded by the hippocampus. And then the complementary system, and the idea is that the hippocampus is sending out these memories over time through a process called replay to the cortex, and that the cortex is building these, is slowly building, layering these memories on top of each other and building a generalized conception that relates these different memories. So you guys learned about patient HM because the hippocampus, as you know, is involved, well, in everything these days, but was originally thought, or for a long time thought to be involved in episodic memory only. That's because of its structure, which gives it properties somewhat like hot field networks have, where you can be given a partial input and the hot field network will reconstruct that input. I believe you guys learned about that. But anyway, let's see, the idea is, okay, so I want to talk about replay just because replay could be part of the story of eligibility traces. So replay was discovered in rodents on performing maze tasks. And the idea is that in the hippocampus, there are these cells called place cells that let's say a rodent is, I lost my animation, is running along the track. These different cells will fire at different places along the track. And then if the animal runs the track again, you see these cells will fire on the same places. But then later when the animal is resting, what you see is what's called replay during what are called these sharp wave ripples in the local field potential signal. When the animal's resting or eating later, these sequences will essentially replay, sometimes sped up, so sometimes condensed in time, but sometimes they're actually reversed as well or slowed down. So there's a variety of different kinds of replay, but this is evidence for the complementary learning system, right? So I showed you before that, while it's learning, these individual experiences are being stored. And while it's resting, perhaps what this is doing, these are hippocampal cells, is replaying this to the cortex, right, for generalization. All right, bye, Aaron, thank you. Okay, so anyway, the idea of replay is now standard also in deep learning networks and has been used in, I think the first time it was really used successfully was the deep Q, what's called the DQN or deep Q network, which learned to play a bunch of Atari games. And a lot of the success they attributed to instigating this replay buffer where it would replay random sequences into the model that they were using to learn the all of the games. And that led to better generalization and much better performance through a process of generalization. Okay, so that is all I have. And really, it was just kind of a tour in order to think more about, what might be going on with these eligibility traces. So, the wild half-baked idea, is that one could say, right? So when I finish building my treehouse, that activates it through let's say replay, right? It activates these episodic memories of the steps, whether it's in my conscious awareness or not. It sort of activates these unconscious memories, the steps that I made, and can evaluate them by replaying them, right? So I could be using my episodic memory and reinstating that. And so those two neurons that were firing together when I originally performed the action and maybe didn't get immediate feedback, are reinstated through replay, but now I've finished the treehouse and I feel good, and all of those actions are being re-tagged, right? So that they can be reinstated over a short time period. So then it kind of gets rid of the long-term tracking, if that makes sense. And that is just a ridiculous hearsay, but
I don't think is ridiculous at all. I think that whatever upcoming models of artificial general intelligence will actually explain this, will probably go through these metaphors. I was just taking note of the things you said, like the episodic. So this is bleeding edge, guys. I mean, you saw the references that Paul's using is like most of them like a few years ago. All of the resources the computing brain uses are old resources, because I want to make sure that everybody's on the same page with respect to the foundations. But this is the exciting space, right? So episodic memory saving, like the replay in your own brain. So the spontaneous activity that the brain is producing. I think that, the artificial general intelligence is not going to go Aaron's, causality way. I think it's, we need some sort of thought pumps. We need more spontaneous activity. We need ways for the system to inspect itself and to create these activity traces. In a randomly recurrent neural network, you have these attractor landscapes, and I mentioned these manifolds that exist even if you just cobble the neurons together. Now, the funny thing is that then if you give a little bit of input to those networks, it will go there, right? And so even a little bit of noise will make the network go where it's likely to go. That's why we keep on converging to the same ideas, or keep on converging to the same value evaluations of our own action. That's why we bash ourselves, right? I mean, we think, I should have done differently again. It's because we are a bunch of these episodic replay attractor type beings that we have to now start to model and in as much of a bottom-up robotic style way as we can. I love that so many of the mentions you had today, Paul, were so beautifully connected to some of the projects that the students will go through. One of them is the reinforcement learning one-arm bandit. So I have, so I think Isa, and who else is on the, Eva? Eva, you're in the, which project did you take, Eva?
I am in the epilepsy project.
Yeah, exactly. So, good, because I also told them to spread apart with respect to their backgrounds. But I was going to say, I get them modeling the matching law, so the law of effect via the perceptron. And why do we need LSTMs for that? So I was curious, but in any case, so these little components that are going to be the final projects tie in with many of the topics that you exposed to us today.
Oh, good. Yeah.
I just wanted to wrap with the happy thought of having how is it that this comes together. I hope that you students, you also see it. I see some of you mildly nodding. Now, I'll stop talking and I'll make a very long and comfortable silence before we go for long words, because this is the time that you should speak your hearts. What are the things that you find interesting, difficult, complex? Where are you? What would you do now, like students, if you took up a research route? And you said, like, what do you find interesting? Where would you deepen yourselves in knowledge? Use the time to get some conversation going. So also I'm going to start like telling Paul about your cool projects. And I noticed that Rianne smiled there because she has a Hopfield network hooked to a categorizing network. So basically a perceptron hooked to an RNN.
Are you guys writing all this code yourselves?
I'm forcing them to.
That's awesome. see some
I'm trying.
single tears.
Yeah, and so from them, I think multiple tears.
Yeah. I'd be, yeah, I would be too.
And I think that this is, the small steps. So I think the computing brain is really, I mean, we have these large scale metaphors, and there are a lot of people that are very good with engineering that can do it. But I think that the fundamental ideas are all available and tackleable. So I don't know if within the span of 2 weeks, this is meaningful, but they've been looking into bits and pieces of code that I also think that they can snip it and take from different places. And then ultimately, so much of it is the level of metaphor, right? So where is metacognition? Where is the reward encoded? How is the reward encoded? What types of time constants are involved? Right, it's fast and slow. How do you make fast? Fast you make with spikes. How do you make slow? Well, slow, it's a bit more complex. You have very many types of slow. You have like consolidation after sleep, right? And so I would just have kids screaming very loudly in my backyard here, so I apologize if I'm derailed. But bringing these threads together is what I would like you to feel you can now do. And this is the time to ask some more questions if you like to, because I'm very good at giving final words and then I never end unless I'm interrupted. Any final thoughts? Sandra? One thing we can do is the what did you get from today exercise. So if you had to summarize what the last 2 hours were about, everybody thinks about a summary. Let's have a little bit of that. And then I'm gonna name names before you step out of the Zoom. So Hiani, you spoke very little today. I am curious, how would you summarize the last lecture? What are your take-home messages? She's searching for the microphone, I think. All right.
Before she begins, I'll just say that I feel happy for you guys to be learning the stuff that Mario has been teaching you, and you've been learning. I don't know. I mean, obviously, I'm biased, but I wish I had learned this stuff at your ripe young ages. And I had no idea what I was really interested in at that point, and it's just so cool. So I hope that you are enjoying what's being taught in the course. I'm sure it's super challenging, but
are you enjoying with thumbs up? Are you not enjoying with thumbs down?
Oh, they have to go. They have to do thumbs up. Yeah.
See, that's my reward. Anyways, this is the motivation to do it. I wanted to be exposed to these ideas. It's a mad ride. It's a wild ride. There's no doubt. And I told them from the beginning, it's like, you're going to be confronted with a host of new metaphors and try to make sense of all this. It's impossible in 2 months, really. And that should not even be your personal goals. Your personal goals should be put yourselves in the stream and let it percolate through you guys, because it's going to make sense. Like the longer you work on this, the more sense it will make. And I hope that you establish some of these foundations. Paul, like it was brilliant. I thought, see, we never met in person, Paul and I. It's like just through this. But listen to the podcast and get your favorite speakers. Think of them. Think of your favorite speakers as your next supervisor. Think of or the topics. Think that you can intersect in the field right now just by thinking. It's a very lovely time in your lives and in the 21st century too. Okay, Rianne, did you find your microphone?
Yeah, it's a bit of a struggle. I'm trying out some new things in my room and it wasn't working, and then I had to update my laptop, so I'm switching to the sound of my laptop right now, and now it's working.
So what was the main message for you today? Or what for you subjectively?
Well, I think it's always difficult to just point out one single thing if you've been having lectures about reinforcement learning for 5 hours now. So I couldn't really point out one single thing. And otherwise I'm just summing up definitions and saying, oh, the value function, how reward can be looked at via eligibility traces, and I don't think that that's really adding to anything. What I did like was the notion of how a good working memory actually slows down reinforcement learning. I never thought about that, but I did like that notion.
It's very cool. I think it's a great note to stop on. I mean, you're all being, think that you're the learning machines. Never forget to introspect as well. I mean, like, we learned a lot and we've got concepts, but try to make sense of them with respect to ourselves, because ultimately that's what you're trying to explain, and you are the best model experiment and observable that you have. So 5 hours of reinforcement learning is we're truly reinforcing it. Thank you, Rihanna. Thank you, Paul, for being here. I don't know if anyone else would have extra few words. Else, I'll get in touch with you, Paul, and I'll see everybody else on Thursday.
Thanks, guys, for being here. I hope it was useful and somewhat entertaining and thought-provoking. But yeah, otherwise, have a great time and good luck.
I think it definitely was. So thank you so much. Thank you, everybody.
Mario, should I hang on here or
hang on for a second?
Okay.
Let's just collect a few thoughts after this, and I'll talk to you all on Thursday. Have a good time, everybody. Bye. Thanks for being here.
Bye-bye.
Thank you.
Bye.